1 minute ago, satellite images captured something impossible happening beneath California's farmland. The ground is collapsing at a rate that defies belief. Entire valleys are sinking faster than geologists thought physically possible. This is not erosion. This is not measurement error. This is America's most productive agricultural region vanishing downward into itself, and the world has barely noticed. What is pulling the Earth down? Why can no one stop it? And what happens when the ground beneath our food supply stops holding water forever? California's Central Valley stretches 450 miles through the state's agricultural heart. Beneath ordinary fields and orchards lies an aquifer system that once held enough water to flood the entire valley 20 feet deep. According to the United States Geological Survey, the valley produces over 1/4 of America's food. Almonds, grapes, tomatoes, pistachios, dairy products all depend on water drawn from hundreds of feet below the surface. But something has gone catastrophically wrong beneath those farms. NASA satellite data analyzed by the Jet Propulsion Laboratory shows land subsiding at rates exceeding 2 feet per year in some locations. Between 2007 and 2010, certain areas sank nearly 3 feet. By 2017, sections near Corcoran had dropped over 12 feet since the 1950s. In places like El Nido, the ground is collapsing into bowl-shaped depressions, creating landscapes that resemble craters more than farmland. This is not a temporary dip. The sinking has already damaged critical infrastructure serving millions of people. The California Aqueduct, a vital artery moving water across the state, has lost up to 20% of its carrying capacity due to subsidence-induced warping. The Friant-Kern Canal, stretching 152 miles and serving over 1 million acres of farmland, has lost more than 60% of its design capacity in some sections. Repairs exceed $500 million, yet engineers privately admit the fixes are temporary. The ground will keep sinking. The valley's aquifer system developed over millennia as Sierra Nevada snowmelt percolated through layers of sand, gravel, and clay. These underground deposits, stacked hundreds of feet deep, form a natural reservoir. Water fills the tiny spaces between sediment grains, creating storage capacity measured in trillions of gallons. The system functions like a giant sponge. During wet years, snowmelt and rainfall soak into the ground, recharging the aquifer. During dry years, water can be pumped out to irrigate crops. For thousands of years, this balance held. Clay layers deposited by ancient lakes act as confining units that trap water under pressure. The famous Corcoran clay, laid down by a prehistoric lake, stretches across much of the southern valley. It separates shallow and deep aquifer zones. Sand and gravel layers allow water to flow freely. Clay layers slow its movement and trap pressure. When functioning properly, the system rebounds elastically. Pumping water out compresses sediments slightly. When water recharges, the sediments expand back to their original configuration. Healthy aquifers breathe. Large-scale groundwater pumping began in the 1920s as farmers drilled wells to supplement surface water. By the 1950s, thousands of wells were extracting water faster than nature could replenish it. Between 1926 and 1970, parts of the valley sank over 9 meters, according to USGS reports. The subsidence was so dramatic that a famous photograph shows a telephone pole with markings indicating the land had dropped 28 feet. The pole remained anchored in bedrock, while the surface fell away. Then, in the 1960s and 1970s, massive state and federal water projects came online. The California State Water Project and the Central Valley Project diverted surface water from northern rivers into the valley. Groundwater levels stabilized, subsidence slowed. For decades, it seemed the crisis had been managed. But that reprieve was an illusion. Starting in the mid-2000s, California entered a prolonged drought. Surface water deliveries collapsed. According to the California Department of Water Resources, allocations to agricultural contractors dropped to as low as 5% in some years. Farmers had no choice but to return to groundwater pumping on a scale never before attempted. During the 2012 to 2016 drought, an estimated 40 cubic kilometers of groundwater vanished from the valley. Wells that had been idle for decades roared back to life. The aquifer could not withstand the onslaught.
Scientists from Stanford University and NASA used interferometric synthetic aperture radar, or InSAR, to measure ground deformation with millimeter-level precision. Satellites bounce radar signals off the Earth's surface. By comparing images taken months apart, researchers calculate vertical displacement. The European Space Agency's Sentinel-1 satellite provided unprecedented coverage. Between May 2015 and September 2016 alone, NASA documented subsidence rates approaching 600 millimeters per year in some worst-hit zones.
USGS extensometers, devices drilled hundreds of feet underground to measure compaction, confirmed the satellite findings. Continuous GPS stations operated by multiple agencies tracked subsidence in real time. Spirit leveling surveys, where technicians measure elevation changes along highways and canals, validated the satellite and GPS data. Every measurement method pointed to the same terrifying conclusion: the valley was collapsing faster than ever recorded. What took 50 years to sink from the 1920s to the 1970s, the valley repeated in just 16 years between 2007 and 2023. Areas that had stabilized for decades suddenly dropped again. New subsidence zones emerged in places like Madeira that had never experienced significant sinking before. The geographic footprint of collapse expanded north and south, engulfing previously stable farmland. Scientists call this acceleration unprecedented. The damage is appearing everywhere infrastructure crosses subsiding ground. The California Aqueduct, which carries water from the Sacramento-San Joaquin Delta to Southern California, runs straight through the worst subsidence zones. Surveys conducted in 2019 revealed that stretches near Huron have warped into undulating bowls. Water flow slows as the canal bottom rises relative to its banks. Freeboard, the critical safety margin between water level and the top of the canal, has shrunk dangerously. The Friant-Kern Canal tells an even grimmer story. Built in 1951 at a cost of $60 million, the canal once moved 4,000 cubic feet per second through its middle reach. By 2017, subsidence had reduced that capacity to 1,600 cubic feet per second in the most damaged sections. Entire segments sank 12 feet, creating bottlenecks where water cannot flow. In January 2022, officials broke ground on a $500 million repair project to rebuild 33 miles of canal. Phase 1 alone cost $292 million. But engineers know the truth. Repairs only buy time. The ground will keep sinking. Within decades, these canals may need to be rebuilt entirely or abandoned. The California Department of Water Resources estimates that state and federal agencies have spent over $100 million on subsidence-related repairs since the 1960s. That figure will multiply as infrastructure continues to fail. Roads buckle, bridges warp, pipelines crack. Every structure built on assumptions of stable ground faces accelerating stress. Meanwhile, the race to drill deeper wells has become desperate. During the 2012 to 2016 drought, well drilling applications surged. Farmers who had relied on shallow wells for generations watched their pumps suck air. Companies reported drilling new agricultural wells to depths exceeding 2,000 feet, chasing water layers that may have been deposited before the last ice age. Costs for a single agricultural well can reach $600,000. Domestic wells, serving individual homes, typically cost $30,000 to $100,000 to drill or deepen. For wealthy agricultural operations, this is a solvable problem. For small farmers and rural homeowners, it is catastrophic. According to reports compiled by the California Department of Water Resources, over 5,000 wells went dry between 2012 and 2022. The majority served rural, low-income communities. Families in places like Tombstone Territory near Fresno and towns across Tulare County woke up to find their taps producing nothing. No water to drink, no water to shower, no water to flush toilets. Relief comes in the form of plastic tanks. In the unincorporated community of East Porterville, rows of white polyethylene tanks sit outside mobile homes.
Each holds 2,500 gallons. Trucks deliver water every few weeks. Residents ration showers and reuse dishwater. Children learn to flush toilets only when necessary. "We watch every drop," one resident told reporters. "You don't think about water until it's gone." Local officials describe a silent abandonment. Families pack up and leave without reporting their dry wells. The official count of failed wells is likely a fraction of the true number. Community Water Center estimates suggest 12,000 domestic wells in the Central Valley may be at risk. A 2020 study published in Earth's Future found that up to 1 in 5 wells in the valley's southern reaches ran dry during peak drought. Shallow domestic wells, which serve individual homes, failed in disproportionate numbers because they tap the uppermost, most depleted aquifer zones. The wealthy drill deeper, the poor go without. Beneath all the infrastructure damage and social upheaval lies the true catastrophe. Clay layers deep underground are undergoing permanent, irreversible compaction. To understand why, imagine clay particles as microscopic dinner plates. When originally deposited, they settle in random orientations, stacked haphazardly like dishes piled in a sink. This random arrangement creates abundant pore space where water can reside. Water pressure within these pores helps hold the clay structure open. But when groundwater levels drop below a critical threshold, something changes at the molecular level. The water pressure that kept the clay grains apart disappears. Stress from the overlying rock forces the clay particles to rearrange. They rotate into parallel stacks, like plates neatly arranged in a cupboard. This new configuration is far more compact. The spaces between grains shrink. Storage capacity vanishes. And the process cannot be reversed.
Once clay compacts beyond its pre-consolidation stress, the threshold marking its previous lowest groundwater level, the rearrangement is permanent. Even if water levels rise again, the clay will not expand back to its original volume. According to Stanford researchers Rosemary Knight and Ryan Smith, who published findings in Water Resources Research, the San Joaquin Valley permanently lost between 336,000 and 606,000 acre-feet of natural storage capacity just during the 2007 to 2010 drought. An acre-foot equals 326,000 gallons. That storage is gone forever. Subsequent studies examining the 2012 to 2016 drought estimated an additional loss of 400,000 to 3,250,000 acre-feet of permanent storage capacity. Combining both drought periods, researchers calculated that 2 to 5% of the entire aquifer system's storage capacity has been destroyed. The valley's underground reservoir, built over thousands of years, is being dismantled in decades. Scientists describe it as drinking from an ever-thinning straw. As clay compacts, not only does storage capacity disappear, but extracting remaining water becomes exponentially harder. Pumps must work against greater resistance. Energy costs soar. Wells that once flowed freely now struggle to deliver water. What makes this crisis uniquely terrifying is that subsidence does not stop when pumping stops. Deep clay layers respond to pressure changes with a time lag measured in months or years. Researchers studying GPS and extensometer data found that subsidence continued for 12 to 18 months after groundwater levels began recovering following the 2015 wet winter. The clay layers were still equilibrating, still compacting, still settling into their new, denser configuration. This delayed response means that damage occurring today reflects pumping decisions made years ago, and current pumping will drive subsidence for years into the future, even if every well shut down tomorrow. The system has momentum. It cannot be stopped instantly, only gradually slowed over decades. Stanford hydrologists used advanced models to project future subsidence scenarios, even under optimistic assumptions where groundwater levels stabilize at 2019 conditions. The valley will continue sinking for decades as deep clay layers catch up to current stress levels.
Under business-as-usual scenarios, where pumping continues at recent rates, models predict subsidence could persist for a century or longer. Some areas may eventually sink an additional 10 to 15 feet beyond current levels. There is no scenario in which the valley returns to its pre-1920s elevation. That ground is gone. The question is only how much more will be lost. The Sustainable Groundwater Management Act, passed in 2014, represents California's most ambitious attempt to regulate groundwater extraction. The law requires local agencies to develop sustainability plans that bring groundwater basins into balance by 2040. On paper, this sounds like salvation, but researchers analyzing the submitted plans found a fundamental flaw. The plans define sustainability primarily as stabilizing groundwater levels, not as protecting aquifer storage capacity. These are not the same thing.
A 2023 study published in Scientific Reports examined 60 groundwater sustainability plans covering the Central Valley. Researchers calculated that even if all plans achieved their stated minimum thresholds, over 9,000 domestic wells and 1,000 public supply wells would fail. 32% of analyzed domestic wells would either run dry or become partially dewatered. The plans allow groundwater levels to drop to depths that will cause catastrophic well failures for the most vulnerable communities. Moreover, stabilizing groundwater levels does nothing to reverse clay compaction. The storage capacity already lost is irretrievable. Future recharge will fill a smaller container. The valley's underground reservoir has shrunk permanently. Even if rainfall increases, even if snowpack doubles, the aquifer cannot hold what it once did. Policy is chasing a moving target while ignoring the permanent loss beneath its feet. The valley is trapped in a vicious feedback loop with no clear exit. Climate change is reducing Sierra Nevada snowpack, the primary source of natural recharge. Reduced snowpack means less surface water. Less surface water forces more groundwater pumping. More pumping accelerates subsidence. Subsidence damages canals, reducing surface water delivery capacity. Reduced delivery capacity forces even more pumping. Each turn of the cycle tightens the spiral. Each drought amplifies the damage. Wet years provide temporary relief, but groundwater levels never fully recover before the next dry period begins. The aquifer operates in a permanent deficit. According to NOAA data, the valley has been in one of the driest periods in at least a millennium. Climate projections suggest these conditions will intensify. The valley is not unique. Aquifer depletion afflicts regions worldwide. The North China Plain, the Indo-Gangetic Basin in India, and the High Plains Aquifer in America's Midwest all face similar crises. But nowhere else combines the scale of California's agricultural output, the depth of its overdraft, and the severity of its clay compaction. The Central Valley is a preview of what happens when industrial agriculture exhausts the underground water bank. And there are no external solutions. No other water source exists to replace the vanishing groundwater. The Colorado River is overallocated. Desalination is prohibitively expensive for inland agriculture. Water markets cannot create supply that does not exist. The valley must live within the limits of what its aquifers can provide, or shrink its agricultural footprint. That is the choice no one wants to acknowledge. The natural storage capacity that took millennia to develop is being destroyed in a human lifetime. More rain will not fix this. The underground reservoir has been permanently downsized. The valley's hidden water vault, the geological inheritance that made industrial agriculture possible, is collapsing from within. Future generations will inherit an aquifer system diminished in capacity, stressed beyond recovery, incapable of supporting the agricultural empire built upon it. Can agriculture survive on land that keeps sinking? What happens when the infrastructure designed to move water structurally fails? How will food prices respond when 1/4 of America's produce comes from ground that can no longer hold water? Right now, California's Central Valley produces food for hundreds of millions of people. Beneath those fields, an invisible catastrophe is unfolding. The ground has sunk up to 28 feet in some locations since the 1920s. Satellite measurements show continued subsidence exceeding 20 centimeters per year in the worst zones. Over 5,000 wells have gone dry, with thousands more at risk. Infrastructure repairs have cost over $100 million and will cost billions more. 2 to 5% of total aquifer storage capacity has been permanently destroyed. Scientists know the aquifer system is compacting irreversibly. They know subsidence will continue for decades even if pumping stops today. They know clay layers hundreds of feet underground are rearranging into configurations that cannot expand back. What remains unknown is when the system reaches a point of no return. What remains uncertain is how many more feet the valley will sink. What remains unanswered is whether agriculture and civilization can coexist on land where the ground itself is disappearing. This is not a story of villains. It is a story of delayed consequences meeting immovable geology. For a century, the valley extracted its future. Now that future has arrived, and the earth is collecting its debt. The ground beneath America's farmland is sending a message in the language of collapsing aquifers and failing infrastructure. The only question left is whether anyone is listening before the floor beneath us gives way completely.